Okay, this is about what happens in an elevator if it's accelerating to the weight registered on a scale. So shown here in the picture is an elevator. It's a larger rectangle here, accelerating as shown upward here. Inside the elevator is a scale. On the scale is a mass, little m. If we do a free body diagram for this mass, little m, is also accelerating upwards with an acceleration of a, um, and therefore the net force has to be upward. There are two forces acting on little m, the gravitational force downward and the normal force of the scale acting on little m that's upward. So the normal force is larger than the gravitational force. To be consistent with Newton's second law, to give an acceleration in the upward direction, that has to be true. So if we write the Newton number 2 corresponding with this free body diagram, that would be the normal force of the scale on the mass minus the weight, m times g is equal to m times a sub y. Solving for the normal force of the scale on the mass, that's going to be mg plus may, which is m times the quantity of g plus ay. So that means that if we know what the magnitude of the acceleration is, then we know what this little n is, and it's in the upward direction. If it's the normal force of the scale acting on the mass, however, by Newton's third law, the reaction force to this, obtained by switching object and agent, is the normal force of the mass on the scale. That's going to be minus n times g. And so let's suppose that we had a 1 kilogram mass. Assuming a g of 10 meters per second, on a scale that's set on terra firma, that scale would register 1 kilogram times 10 meters per second, which would be 10 newtons. If we suppose that we have an elevator that's accelerating upwards with 5 meters per second, as shown here, and we take g equal to 10, then the normal force of the scale on the mass is g plus that upward acceleration. In other words, it's 10 plus 5, which is 15. 1 times 15 is 15 newtons. That's the normal force of the scale on the elevator. Again, by Newton number 3, the normal force of the mass on the scale is the weight registered on the scale, and that's 15 newtons. The weight has increased as a result of the 5 meter per second upward acceleration. On the other hand, if the elevator is accelerating down, minus 5 meters per second j hat, instead of up, then what will happen algebraically is the normal force will be, instead of being g plus 5, it's g minus 5. And so now the weight registered is 5 newtons. The mass is lighter. If we take this to the limit and we have a upward acceleration of the elevator, a downward acceleration of the elevator, I should say, of g, minus g times j hat would represent the elevator accelerating downward at 10 meters per second. Well, that would correspond physically to somebody having cut the cable to the elevator. It's in free fall. Then, if we have an an acceleration of minus g, the normal force, that should be an n here, is 0 newtons. And by Newton number 3, that means that there's no force that the mass can exert on the scale. And so therefore, in a elevator with a cable that's been cut, you would not register any weight if you stood on a scale. Fourth scenario, imagine the elevator is going up or down at constant speed. What then would be the weight registered by a 1 kilogram mass?